Okay, I think we'll get started. So, good morning, everyone. My name is James Richings. I am leading today's part of this course. We will cover sort of three main areas: templating, lambda functions, and standard algorithms. We'll split this up. So first, I think it'd be useful to go through the example from yesterday and spend probably 20 minutes to half an hour on that. We'll then sort of discuss a brief introduction to templating, and I have a sort of it's not in the course materials, but a simple example we can either work through or people can have a go during the break, and then we can come back to just afterwards. We'll then discuss lambda functions or closures, and finally how they can be used in conjunction with some of the algorithms in the standard library. And then there is an exercise for people to look at sort of after that, and I will come back tomorrow morning and discuss that example in some detail. Okay, to get this started, let me just share my screen. See a terminal interface with sort of split in half. I can see it here. Please put any questions in the chat that you might have. I will do my best to answer as we go along. Don't worry if they seem like things that are obvious. Any questions are useful. Is this the right version I wanted to have here? Yes, it is. Okay. So in this example, so there's two steps to this. The first one is this implementation requires that the size of this object be a power of 2. The matrix does not need to be resizable. And the most important thing is the matrix must be must not be implicitly copyable, but must be explicitly duplicate by a member function. And this is to get us to play around with how the rule of 5 works and how we can generate classes which have certain behaviors based on the constructors and the destructors and assignments. So I'm going to try and code along here, and please jump in if I do something particularly stupid. The first thing we need to do is look at the sort of data member, how we're going to store the information. So this is the first to do we start with. One thing I should highlight here is that this example was originally written with templating involved already, even though we've not quite discussed it. So the most important thing for now to think about is anytime you see a capital T in this example, you could just think double or float or int. It doesn't, it's just a template parameter, sorry, it's just a wildcard, for example, for any type. And we'll discuss the details of how we do this ourselves after this example. So what we can start with is we're going to here use a standard unique pointer. And we want to be put over an array, but it's an array of type T. So in this case, in an example, we'd say an array of doubles. Okay. We're going to use this. We could also use standard vector, but we'll come on to the differences in the choices there. So this is going to store our data for our matrix. And we have the rank of the matrix is a square matrix, so we only need one variable to store that. Now, if we look at the constructors, we need to think about is the default constructor for a unique pointer the correct thing to do here? So if we look at our CPP reference, and I'm looking at, let's go back one. So this is the page, CPP ref, talking about unique pointers. And if I just go down to constructors, and it's number 1 that we want, so it can construct a standard unique pointer that owns nothing. So that's the default. So sorry, that's a no value initialized. So we can use the default without any concern here, which means that we don't need to add anything to this section here. So we've done this to do. However, we will need, check my notes, to allocate some memory to initialize this with some value, visual values. So to do that, we just want to set our rank for the value R and the data to have some new array. So our unique pointer is going to take a new array of type T, and the size of this is going to be R times R. So what we're going to do is we're going to encode this two-dimensional matrix into a single array, and then we have some encoder and decoder functions that is provided by the bits that does the Morton ordering for us. So all the bit fiddling is done. But we can use to translate between this two-dimensional and one-dimensional representation. So that for now. Okay, so and then we have an assert here just to confirm that we could only go by powers of 2 as we wanted to. And that's the constructors. We then have implicit and copying is not allowed, which is one of our requirements. So we're going to delete the copy constructor and copy assignment here explicitly, just by putting them equal to delete. So they don't exist. So you can't accidentally copy. Is moving allowed? What we said it was, but will the default moving behavior, is that enough for us? So if we go to, again, back to our unique pointer, we can then look at whether movement as it's defined in the default is acceptable to us in terms of what we want this matrix class to do. And if we read the CPP ref, construct a unique pointer by transferring ownership from U to this. Stores no pointer in the previous member U. So that is a sensible set of behavior. So then we could just use the unique, the default behavior in this case. So to do this, you can just set it both default. Or I forget, because we're using a unique pointer, we need to include right. Likewise, we can just use the default behavior for the destructor as well. Okay, so we need to then look at notes. Other than access. So we will come back to duplication in a moment, but first let's look at how we're going to access the element inside this matrix to be able to actually use them and update them. So we have a constant, a mutable version of this function. You're screaming at me, right? So to do this, we can use the functions in the bit file here. And what we're going to use is we're going to encode. So we want to have an X and a Y component, and we want it to return us as the position Z in the array data and return that value. So then this simply becomes auto Z, which is our output, of course, encode Y. Okay, and so we don't want the position, we want the element itself. And then to do this for the other cases the same, we can just copy and paste this here. Okay, and then raw data access. Similarly, we have a constant immutable version of this. We need to use the of the unique pointer. And this is simply just return data. So the unique pointer is itself, the data is as a function get, which gives us the raw pointer. This is then okay. These to-dos. So we have a unique pointer that we know how to access elements from, and we know how to provide the access to the underlying data members. What we haven't implemented yet is a duplicate function. Now, this we're going to have a matrix. Simply answer rank and the standard copy. To test the data. And this is then everything we'll come on to later is around we're putting in the initial position. We're going to we're then going to provide data plus the size as the end position. And we're going to provide pointer answer. That. This is where I will make with errors. I was not declaring this scope. And fine. here the private member is. That data is going to return itself. So data is not going to provide the pointer I want. Thing. Okay. And we can then just run this. Then all our tests pass for that step one. Okay. Are there any questions of that section? Okay, if I don't hear anything, I will keep going. Step 2 of this then looks at the between the implicit copy and our duplicate function. Okay. You have to actively call the copy, the duplicate function by hand. You're not going to implicitly copy it because you've called. It's going to happen as an active thing that you have to type it. Basically, you're not going to have accidentally copied because this could have performance implications in your application. So if you're going to do this, you really do want it to be somewhere where you identify that you've called this. There's a danger that you have copies happening that you don't expect because of the default behavior occurring. And what this does is put a barrier for you doing that and hopefully reduces any chance of any performance-related impacts, really. This is an example. This is just playing around with one way you can edit these operations. Okay. Hopefully that answers your question. Everyone see my video okay? I'm getting told I have poor connectivity, even though I'm sat right next to my router. No one's screaming at me, I will keep going. And in this case, we're doing something very similar. I'm just for sense of time, I'm going to go through this a little bit quicker. There are solutions up on the GitHub under a separate branch for those who want to go through in detail. What we're looking at here is that you have a very similar class as before. Let me just get my notes up. But this time we are using iterators to do this. So you see this function duplicate that we just used instead of looking at the data and finding the pointers exactly. We're using the iterator syntax in order to do the same operations. So we're looking at generating the begin and end functions of an iterator. We're also looking at so we have the using function, so iterate, we'll come on to discuss this, but the iterator is set as a matrix iterator, and our job here is to really implement this matrix iterator itself. and how you set one of these up. So I think a key thing to sort of kind of note is that we're using this syntax, and it's a little bit in flux. I think this has been removed from later versions of the standard, or not sort of deprecated, but a lot of code has used this sort of as a template, or as a template is a bad word in this context, but a pattern to use. And the exercise is really around going around and implementing all the necessary components to have an iterator you can use in order to use to move through your matrix or a container of matrices using iterators instead. I think, considering we're almost at 10 o'clock, I'm going to leave that as something you guys can review in the solutions and move on to the templating section of the course, because there is an example of that I'd like to discuss before we go to break at 11 o'clock. And you see, so what are templates? Why would we want to use them? What's kind of the motivation here? This is meta programming. You're not writing. The idea of templates is to not have to write the same piece of code over and over again, which effectively does the same thing but has slightly different types. So the example we had, I think, earlier in the week was sums, and here we'd have to write two implementations of the same sum for two different types. And you can see this getting very dull by the time you implement this for however many variations. It becomes quite a lot to maintain. And in the simple case of a sum, it's not really an issue, but you could imagine there's lots of cases where you could have complex functionality you need to operate in the same way across multiple different types. And this becomes a lot to manage, where you'd actually want to use something to generate this code for you. Okay. So this is where template functions come in. Also, templating comes in. There's template functions, and we'll talk about template classes as well. So we follow this syntax. We decorate sort of a template, and we have some angle brackets which define a type name. This could be type name or class, and then this is the wildcard parameter that's then used that will be replaced by the compiler for when it detects a particular usage of this pattern. So here below you can see an example for an unsigned under float. You explicitly tell the compiler which you're going to use, and it will generate the code for that. Oh, my mouse is doing crazy things. Interesting. Good, that stopped. So here in this sum example at the top, we have t is the return type of a function, template function sum, and it takes a t typed value a and a t typed value b and returns the addition of them, which is some new scroll. Okay. I don't have to explicitly put into in some cases the compiler can deduce this for you, but it's useful to include it to demonstrate intent and clearly help yourself understand that you've used a template function. I think one thing with these, they can be kind of more difficult to debug because you are letting the compiler generate code, and when it throws errors, they can be a little bit more obtuse and hard to understand where the actual error is coming from. And by I would kind of not try to hide this in so as much, give yourself as much information as possible, really. Okay, we can also, so that was a template function, but separately you can have template classes. Here is an example that will produce a simple myArray, but now you have for any type T. Here we've used class for T instead of type name. I think it's important to understand that this is kind of a useful concept to get in your heads, is the idea that these are interchangeable, because a type is just some definition of some so any class can form it's a type of some object. It's useful to leave them as, to pick a convention and stick with it. I slightly prefer type name because it is a sort of separate syntax, and it's slightly less confusing, but consistency across a code base is most important. So try to follow whatever convention's been used if you're working on an existing code base, or set one that you prefer and then stick to it. So we also see here the first example of using this sort of T star. So we have a pointer type of a pointer of type T for data, defaulted to null pointer. This is sort of a common theme we'll come on to, is that you can explicitly, you don't just have to use a type template variable on its own, you can also decorate this with other values. So below we also have const T ampersand, so constant reference of type T, and then a constant reference, sorry, a non-constant reference of type T for the for operator square bracket. And we could do a number of things to get related types to T. This can be very useful to be able to use this full set functionality of the type system. Right. The other important thing to, I kind of highlighted a minute ago with the matrix example for modern ordering, is that we can use this using sort of method in order to define type names. This can be incredibly important when you have very long and complicated type concatenation or combinations that you don't want to simplify into something you're actually going to use. This can improve readability. It can help make this much sort of simpler to understand. We saw it in the previous example where we had the matrix iterator of some particular type, and we just called this iterator, and then we could just use iterator through our class, which is much more understandable to someone coming along and trying to read your code, and yourself when you've forgotten what this complicated combination class, so combination type actually is, and what you want it to represent. So the other thing I just want to mention, the other way people sometimes do this is use type def. What it means is that it becomes, if you type def, you kind of have to include the template or the type that you want to call the when you use type def inside, whereas using takes care of this for you. So it's slightly cleaner to use using than type def, notice, but you may see this also used in certain codes. So to have a similar purpose. Okay. So here, for example, here's an example of using. We can just have the value type just equal it to T, the reference type, and the const reference type. And then this is the same example as before, but now it's much more readable in terms of what the intent of each of the return types of these operators are. Okay, so where do you put your implementations for these functions? Templates are not executable code. They tell the compiler how to create executable code. So the definition must be available in each translation unit. So each user of the, so every time the compile is called on the translation unit, it must have access to the templates it wants to use at that time. This is typically in a header file. So you can define functions in place where you have, so here you just have an array class, or you can implement them at the end of the header file. So this is my array constructor. But they need to be in the same file. These are sometimes put in separate files, but they need to be included in the header file. You need to make sure that it's all accessible for each of these, where everywhere you're going to use it, and you can't do this kind of separation that you would normally do between in sort of definition and implementation, as you would do with non-templated code, because you need them to both at the same time. So try to keep them close together, really, or you will start hitting some issues. It will come out as sort of a linking issue. The important thing here is the idea that these are not executable code, and you need to provide everything together, and that it's going to generate something for you, and how good that generation is dependent on the compiler, and there are lots of bugs that you can get into when using templates, and issues where as you've made assumptions about what the compiler is going to do, that you just need to be a little bit wary of when using these. Okay. So kind of one thing here is that you want one definition. So I could write two templates of the same name, two different translations, two different header files, and the compiler will pick one sort of not arbitrarily and use one. And if they've got different implementations, then that will do different things. So this is the one definition rule. Ideally, you want everything defined exactly once. So everything had to be defined exactly once. Here, you need to be careful yourselves and implement exactly once with templates and inline functions, because they may be repeated. And this can mean you'd have varying behavior depending on what the compiler decides to do, what the linkers decides to do, and this could lead to very nasty problems, not understanding why your functionality is not doing something seemingly erroneous, but actually it's just picked the other implementation. The other case here is inline functions, which we won't go into too much detail here, but it's just something to be keep aware of. Okay. So yeah, so we discussed kind of template argument deduction before. So it would the compiler would try to choose T based on the arguments, and try to match the types for you. You can let it do this to a certain extent, but you're using the auto keyword here to know what sort of the type of Z will be, because the deduction, you're not going to know that ahead of time necessarily. So the output of sum will only be determined once the compiler's deduced what T is for this particular case. So using auto will allow the compiler to figure out what the correct type for Z is once the compilation has run. And this template deduction, so you'll see a lot of the times when you have to use auto types for things in order to get this to work correctly. So as we briefly said before, you can template parameters. You have lots of different types of functions with using variations on the original template that you pass in as a sort of wildcard for the type of the input or part of the function, and you can wrap this in various sort of operations or qualifications of the type. This will all affect argument deduction. A classic one you see quite often is standard vector wrapping a type T, because that's quite a common pattern you'll see around. You could, but also all the things we discussed before around constant references, and we also have this case, this forwarding reference, the double ampersand. So you can imagine there's a variety of ways you can manipulate your type variable. I think the other important point to make is that you don't just have to have a single type variable, you can have multiple. Obviously, you don't want to make this too complex, because the work the compiler has to do to deduce what the type should be becomes very complicated. So you should try and keep this as simple as possible. And if you're using that many types, is it really necessary? How much reuse are you really getting? How much overhead and maintenance are you saving yourself if it becomes that complicated? So that's very important to consider when using these. Okay. You can also have some non-type template parameters. Now, this can be useful if you want to ensure, so the things that are currently available in sort of 17, the standards, 17 standard, is integers, pointers, and enums. There's some additional functionality in C++20, but C++20 isn't fully implemented in the standard yet. So not implemented in all compilers yet. So not all the functionality is yet there. The most obvious use case for this is an int, and passing in some fixed size that you're going to do at compile time. So vectors and matrix sizes are a good example here. And at the bottom we have an example of a vector matrix product, which would then have some defined size, which will always abide by these parameters, so that you are always going to match the correct. So you always require that the correct size of vector matrix product is going to work, basically. Okay. The full rules are quite complex of this. So sort of in short, you can ignore all the sort of full complexity and detail and just follow some simple rules and test and iterate and develop your understanding. So whether you want to copy the argument or not, if you don't want to copy, add a reference, basically. What's the relation to? Sorry, 1 second. Yeah, so this case, so this is how do you apply these sort of effects onto your template type. So if you want to copy the argument or not, if you don't want to copy, add a reference. So you can manipulate your usage with the template parameters and hit these real basic rules of thumbs to allow you to apply these to a templated case effectively. So I want to get onto an example for 15 minutes. The auto keyword is using, as we discussed, the same template deduction, so the same type deduction as the templates are. So you often see these used in conjunction, and they're quite important in order to get out some compile time defined type as an output of a templated function. Okay, I wanted to go through a quick example with you. I just need 2 seconds to set this up. So what I was planning to do was go through a simple case. So we could do this in one of two ways. What I think it'd be very useful to do was, if people are keen and they think they understand how this templating works, is to take a simple example like this sort of, not this myArray class, effectively the complex class that we had previously in the week, and write a templated version. So it's not going to be complex, it's going to be some data class, which has a couple of data elements. So there's a couple of member data elements, and effectively implement a very simple addition overload for them with templating. Now, I can either walk through an example I've developed and just discuss what this would kind of look like, or we could spend 10 minutes, 15 minutes, people trying to start this and see what they get. So what would be most useful for people? So by a show of hands in the chat, if that's, would you like to have a go yourselves first, or would you like, and we can discuss any issues people run into, or I can walk through an example. So let's show of hands for trying yourselves. Okay, let's do that. I think let's do that for, yeah, if you guys lower your hands. Okay, then people want me to go through that sort of step by step. Okay, and that's kind of one out. So let's let me try and show you. Let me just find my example first. Yeah, I'm going to try and code this along so that it's a little bit easier to read. Yeah, of course I can next server. So we're going to have a simple structure data. I have numbers x, y of type T, and then you have some default character, and then I'm going to have another one. So I'm going to initialize x, y, y. Getting nothing. This convention. I think this comes from saying these are normally private, but ultimately this is a structure, these are all public. Yeah, so there's no requirement here. Okay, and so then I just want to do a couple of other things. So as part of this, I just want a simple printer. Is And now the kind of the bit what we kind of understand here. So we're also going to have a data. We're going to have an output type, and this is going to be an operator. Plus, and this is going to return. It's going to be one thing, a const. Data name data t by reference, and we're going to call this object. Eventually. Okay. So I'm just going to have a simple thing just to illustrate this a little bit. This is when this is called. And data t. So that's the temp member of this. And then you can say this is all public, so I can just access these. So it's going to take X from this member, this object, and then from the object I'm going to act this operator on. I'm going to return template. Okay, so this is a simple structure, a simple struct that's just got two members. We've got a way of initializing them, we've got a way of printing out their values, and we've got an operator we can overload. Okay, let me just. I'm going to write a simple test. Then, yeah. I've got some template, which is going to take some, again, some T. I don't want to turn anything out. It's just going to be, give it 4. Just for simplicity. It's very like simplistic. Here. So then I'm going to use this to make a member and which just takes A and B to T takes C. Pop this towards T, said, led to that's M. Okay, and then we just use the main function to okay, I'm just going to grab that one. In the input for this. Okay, so this is going to be a simple case of just formats. I won't name this anything. Okay. So if we go back to what this has done is it's so that's the output. Yeah, I'm just going to open the code again. Let me just do something so it's simpler. So what we've done here is we've created a simple templated structure that has two members, x and underscore x and underscore y. We have some initialization, and we have an overloading addition operator. Okay, and this allows me to add two members of the same type together from two different data objects. So, and then in my test, what I'm doing very simply is I'm saying for any type T with four members of those types, I'm going to just make two of these objects and then add them together and print what their values are. So here, this integer example, it's very simple. I said we call the test int. So this is going to make a data struct with type int instead of t. Hi, Marcus. Yes. Do you want to ask a question? No worries. And the point of this is then we can use the overloaded addition operator to add them together, and we can print the result out of that. So this is very simple. We just get 1 plus 3 and 2 plus 4, and we get the result 4 and 6. What we can then do is we can then try and demonstrate that this works for other types to show how this template is kind of working. So I can do something like a float example. Save that. Okay, just go back to code for you. So I'm using an entirely different type, and it still works. It's kind of interesting, but it's not particularly radical. So the other thing we can look at is something like bring kind of a clear example, because you'd never really want to kind of do this. But I mean, these are all kind of points, really, aren't they? So then we could do this, for example, for a string concatenation. And then you end up with A plus C and B plus D. That's because the string has a. What we're relying on here is whatever type we put into as T has some addition operator. Sorry, my mouse is playing up at this screen today, and I don't know why this cast is being so slow. So in the operator overload, when you're adding two data members that we have type whatever we pass in, we need plus to be addition to be well defined for them. For string, let's just concatenate the two members together. For float and int, that makes perfect sense. That's just a mathematical addition, but it gives you an example where you can combine multiple. You can apply the templating to multiple different types and get some sensible result out. What you need to be careful is that the types you then use actually have the set of functionality to do this. So if we then look at something that will break this, well, not break, but it won't be well defined, I do this, and let's do. Are the angle brackets in for data? Yes, because they're saying when I use an instance of this particular structure, I need to pass in the type. Here, I'm passing in explicitly as int and giving an actual type. But here I'm saying use whatever type use the template. So here I'm saying I need the return type to be a data object with whatever type is passed in when this is initialized. But in practice, what happens is when I have my examples below, where these are, so in the test, I pass an int, this t here, in the test case, is turned into an int. It's expecting ints from all these cases, and then this will become an int, and it propagates all the way down. But the same happens inside this class. So then when I have this class, these return types will be ints, data bracket ints. Probably do the deduction in a simple case, but to be explicit, I'm including it everywhere. But in the class, I think you definitely need to keep the angle brackets. Right, I just want to finish off by giving an example of kind of breaks and kind of a warning here. Okay. Save that. Okay. So this gives something undefined print, and this is because you're trying to add two characters together, and that doesn't really, the card doesn't really make sense of that. It's going to do some overloading with the addition operator, which is a bit, it's not going to return a character. So you've got to be careful about what types you use this on when you generate these templated classes, and be wary that it will allow you to do things, and should you do them or not, and it's just going to wildcard for a variety of cases, and it will error in some situations, but because you're generating code, you just be wary of that, because you can do something, is it well defined, and how much will the compiler protect you from that? Okay, I think we don't have an exercise now, but I think now's a good time to take sort of a half an hour break, and then when we come back, we will discuss algorithms and lambda functions. I'll be around for now. If there's any questions, please just put them in the chat, and I'm happy to answer anything people have. Otherwise, we'll start again at 11. You can cast like you can in C. I mean, you have other functions in C++, but you're not really just doing casting. I mean, you could cast the cars into something else, yes. The reason I did something kind of dumb is to demonstrate that this has limitations, and you need to be clear about what operators you are using, and this simple case doesn't kind of account for some edge cases, and that when you're generating this code automatically, there are pitfalls. Yeah, as Nick's indicated, you can just do bracket in X. That's not going to replace what the angle bracket's doing, which is passing a type as a parameter. So Rob has a question around how do we want to treat the copy operator? for the first Morton ordering exercise. Do we usually always want to remove the implicit copy option if dealing with anything larger than simple data types? And if our member variables are unique pointer, do we still need to do it ourselves, or can we leave it to them if we have a unique pointer? That's the second question. There's no sort of default answer to whether you want to remove the copy operator or not. I think the example there is saying is that if you have some large data set where its performance could be performance critical, you don't want to allow someone to come along and use that class and move and allow it to be copied all over the place, because you'll use loads of memory and you're kind of forcing the rest of the program to avoid that by deleting it. You're right, you can use the unique pointer to do this by default because that's its default behavior. I forgot to mention that during our discussion, but I think the original example was written for standard vector. And depending on which by default is copyable, but if we delete it in the matrix, then we can remove that functionality. But there may be cases where you do want to allow explicit copying if you do need to, implicit copying, if you're being careful and you know what's happening or you require it for other reasons. There's no sort of default hard and fast rule with that. The point of this exercise is really to give an example where you do remove some of the functionality and look at the rule of 5. Yeah, that's my understanding as well. Because you can't copy a unique pointer, then you can't, the class above can't. The compiler wouldn't be allowed to make a default implementation. Obviously, you could find a way to get around this by writing your own implementation. I'm sure there's ways to duplicate this, as we've shown, but I mean, the key thing is that that's my understanding, but the key thing is to read the this page. What we have is something like that. Why does the template thing called twice? Is that in something I wrote? I might have mistyped. What's that? The example for the print vector. I'm sorry, it's not very well formatted here, but it's a slightly different for loop structure to iterate over the container. But I don't see anything obviously that's different. For your question around template code before the break, why does the line template T appear twice? Why do you say twice? Is that because I have it on the test as well as on the struct or the class we wrote? if what you're looking, yeah, it's because we've got two separate things going on here. We have a template class data, which is one object, and then we have a separately just a standalone templated function test, which is another thing. They're not related. I finished the class. I could have made it a member of the class or something else, but I wanted to keep the, yeah. I wanted to keep them separate because they give example of both being used in together. I should have made that more explicit. Yeah. Okay, I think that's several people back. I may have lost a few, but okay. Yeah, we tend to do it as a separate line so that the syntax for the struct of the class is on the line below, so that keeps the same information as you'd normally get from if you're just writing a class normally, and then the template goes above. It's just a convention. I think you could just write it as you've written there. Okay. I'm going to get started with the second session. So I gave a bit more time for this one because we have an exercise at the end which goes through some examples, and I've realized I moved the coffee break around a little bit, but I think it will be advantageous as this material is a bit longer. So what we're looking at, that's not what I want to do. I want to select that and then go away. Is iterators. Well, what we're going to look at is standard algorithms. And to start, we're going to think about the ways we can iterate through structures, containers. That's what I'm looking for. And we have kind of three styles that we've discussed so far, or should be kind of aware of, which is the kind of the C style, where we explicitly give a starting point, a condition, and increment. And we have the older style C++, which uses iterators more explicitly, but kind of keeps the same syntax. But you have to dereference the iterator to get the data member you want to operate on inside the for loop. And then we have sort of newer range-based for loops where we act on the item explicitly, and that's much more simplified. We also have standard algorithms, the standard algorithms library. This includes about 100 function templates or that implement algorithms like count the elements that match your criteria or divide the elements based on a condition. These use iterators to specify the data that they work on. So you might count the vectors. So here we have an example. They're included in the algorithms library. I think there's an annoying split here where you have two libraries. There's algorithms and numeric algorithms. So just be wary that some of the functionality where you might think you want is in one and not the other. So here we have count example. We operate on some data, some standard vector called data. We specify the beginning end using the iterator sort of syntax, and we count 0 inside data. So how many zeros are there? We also have a count if, which takes a particular what's called Boolean unary function, I think, that is prime with a function which takes a single argument, or return true or false, and then it enables us to count the number of primes in this data. So you can see this can be quite nice because it simplifies our sort of for loop syntax even further and allows us to do a number of standard operations on a container iterating through. So we could have implemented this ourselves. And we would end up with two templates for an input iterator and a unary predicate. So that's what's looking for. The predicate was the word I was missing there. So it takes one argument, and the predicate means it's a Boolean valued function. So here we're going to iterate through the first to the last elements in this for loop, and at each time we're going to apply the function, the unary predicate, the function p, on our element. We know we're starting, so the for loop here, the structure is slightly different. We're using that older style C++ for loop style. We know we're starting at the beginning, so we've removed the sort of left-hand most element. We just start with a semicolon. We iterate through from first to last, incrementing our answer based on the Boolean result of function p. Okay. There are a number of these algorithms, but here are a key few. So for each, apply a function to each element in the range. That has kind of obvious uses. The count, counting and countif, as we've just discussed. Returns elements matching. Returning a sort of find. Return an iterator to the first element matching or end if no match of a particular, based on a particular operation. Copy, which we already kind of saw earlier, and we can apply a destination. Well, something you can do here is you can also, so you apply a destination. I think the transform is sort of the most powerful here. This allows you to apply a function to an input element, storing in a destination. You can also get it to store into the input as well, using a back inserter. Has an overload to work with two inputs at once as well, so you can have more complicated transformations. Swap, so exchange two values. You may want to provide a way to make your types swappable. So if you implement something, you want to change them around. And then obviously things like sorting. So either using an operator or providing your own conditions. And then upper and lower bounds, which are kind of obvious. So these are kind of very standard things you want to do in an algorithm. But you have the setup to iterate through a container and apply these for you, offered by the standard library. So these could be very useful in a number of ways, and it's up to you how you're going to apply them. So why do we let's look at a simple example. So this is for each, apply a function to every element in the range. So why should we bother with this? It's a very clear statement of intent. As a reader of your code, it's obvious what this is going to do. You're not going to get an off by one error. You're not going to skip elements. It works well with other range-based algorithms. It's concise if your operation is already defined in a function. However, so a range-based for loop can be better, but if you want to communicate and write clear, understandable code about what you're applying, then this can be very useful in writing clean code. Transform is more complicated. Very powerful when it comes with two variants. You can either take a single range apply a function each element, which is similar to for each, but you're storing the output iterator somewhere. And this looks like an equivalent to a map in a functional programming, or map produce. Here, what you need to require is that the range of the output is as big as or greater than the input, because you don't provide an end to the output iterator. But you can do things. So this is double in place, for example. You're going to iterate, double the value, and then place it back in the same location as your input. Okay. Why would you do this opposed to writing your own implementations of these things? They're not particularly difficult necessarily. The patterns, the implementations have been written and tested by your compiler authors, which means that you don't have to support pieces of code. The library's made to be able to do optimizations specific to your platform. The compilers can be very good at this. You're also writing it in a much more sort of human readable form, and you can communicate much easier with sort of programmers what your code is really doing. And it's much simpler to write. So this simple example is just to add through my list of images, does it contain a cat? And then I'm going to add it to my vector of cat pictures. I can do this in a single line, and this is using the back inserter to insert onto a my container cat pics. It's much easier to understand what's going on in the bottom example than in the top one. Okay, so that's a little brief introduction to algorithms. The key thing here is that they've been implemented for you, and that they may gain optimizations by using them that you might have to get into the weeds to get certain benefits from if you implement your own, and then you have to maintain that. So unless there is a strong motivation and a gain you think you'll get from doing it yourself, maybe this is the first port of call. It also looks a lot more like, sort of, if you come from a Python background, this might be a bit more familiar to you. Right. I think one thing I meant to say is that when we've been talking about template arguments, you'd almost never have to put them explicitly in here. See the transform call at the bottom here, we don't actually give the angle brackets because we know we can do the deduction pretty regularly. It's going to be the iterator will be able to be deduced by the compiler. So this is an example where you actually are using templates, but you're not explicitly sort of stating them or giving explicit values to them when you're actually calling the transform function. Just to tie in what we were discussing earlier. Okay, lambda functions. So in the transform example, you're going to need to give a function to operate on. But we'd like to maintain code locality. We want to be able to keep that function close by to where the transformation is happening, so we don't have to go and find a function defined in some header file and its implementation a couple of files away in order to understand what's actually happening in our code, because that reduces readability. But we want some function-like object to pass in. If we have to define functions for one-off use, it's inconvenient, moves the code away from something to discuss. And worse, you could have to create a custom function object class each time you want to implement a particular transformation. So how could we improve that? So let's take an example with sort of worst case first. So this is, we'd have, if we want to do double in place and then we want to add, sorry, not double, we want to square something and add c at a constant. The way the algorithms work is that because they take in they're a unary function, they only take a single argument. We're going to have to define, so we define our function at the bottom here is what we want to call. And we have a vector of floats, which is our answer. And we're going to resize that based on the input vector x. And here we're going to use the transformation. We're going to go to the beginning end of iterator through the container x, the vector of floats. And then we're going to start our answer at the beginning of our answer. And then we are going to apply our square and add a constant function. But in this case, it can't just be a function because we can only pass a single value into here. So actually, we've had to create this structure. And this passing C in is the constructor call to square and add constant, which then is going to be taken as a piece of state. And then when the transformation operates, it's going to call this, the operator, sort of operator brackets on each of the members in the vector x and return the result of that function. So in order to get this additional constant addition on, we've had to implement a whole structure class to get this effect. And that would have potentially to be moved away from where this code is actually being used and makes this less readable and understandable. So it's quite verbose to do this. So we can use lambdas to kind of improve this. They're objects without any name. So you can define them inside a function body, you bind them to a variable, you can call them, you can pass them to other functions. They can also, most importantly, capture local variables. They behave like they have some simple state. You can capture these also by reference, and there's some fancy things where you can capture by reference or by value the current local scope, the value's there, but try to avoid that particular piece of functionality. They have a unique unknown type, so you have to use auto or pass them straight to a template argument itself. But they allow you to capture some information about the local scope and store that as part of the function, which when we talk about standard algorithms can be very useful when they usually take single arguments as they iterate through some container. So here is a less verbose example where we're going to use a lambda. So instead of having our separate structure, we've got the same function as before, standard vector. Is that so that we indicate that it's a float? Yes, but this is just that's a convention. Putting F there is just, if that's what you mean, then that's up to you to decide to do that in your code. If I want to have multiple different types, then I can. I mean, you could argue that actually what I want is a template version of this, which is standard vector T. Use the function I call inside square and constant. In the previous slides. Yes, sorry, I see your point. Yes, it should be yes, square and add constant f. That's just a transposition error, but you see the point. I think it's so that, yeah, otherwise you have this you shouldn't be called, this should not be calling this function because it's got the wrong argument list, and this should have had an F here and therefore be this structure. Okay, that's clear. So instead of that, you can use the lambda to do exactly as we were doing before. So you have a standard vector float, which is your answer,
and you take in the same, you take a constant reference to a vector of floats x, and your float c, which is your constant. You resize the answer to be the same length as your input x. And now the new bit is you have you're going to call it funct, but you can call it anything you like because it's a lambda, an auto to funct that equals square brackets, which is what's called the capture. You then have a list of arguments. So this is a double Z that returns then the function body, which is Z squared plus C. You don't have any concept of exponentiation in C++, so Python uses this might be kind of different. And now, instead of having to, when you call the transform on this, the syntax is the same until the last argument. But this time, see, we haven't had to pass in funct bracket C, because to pass something into the constructor to initialize the constant we're going to use, because we've already captured its value as part of the definition of the lambda function. Then at the end of this scope, we're just going to return the answer, and that lambda function will end its utility. It's just not passed anywhere. Okay, and then we can do this even less verbose, where you don't even define a funct variable which holds the lambda. You just pass it straight into the transform function. So now it's very clear what transform is doing, because the operation which it's performing is defined when it's called, which keeps code locality good, and should be ideally make it more readable and understandable to people who come along and use this program or adapt it, because you kept everything together. Obviously you don't want lambdas to become excessively long. You still want to use the benefits of writing good functions, but for small pieces of code which are not duplicated heavily, these can be good ways to keep code location. Okay, so let's go through some of the anatomy. So at the top here we have kind of the definition of all the parts. So the square brackets is kind of the new, in sort of at the beginning, it's kind of this new piece of syntax which says that this is a lambda expression. This is the capture. This takes in a number of arguments from the local scope. You take your argument list in as normal. See, there's no function name here at all. You then at the end, inside the curly braces, you have your function body, which is what you're executing. You also have that you just write as you would normally do with any function that have a return. You have this new C++11 syntax to specify the return type of the function. So this is this arrow return type, right arrow return type after the argument list. This is, yeah, so it can be, yeah, it can be, it's not, it's sometimes implemented, sometimes not. It can be used. We discussed the captures. So you can capture anything from the local scope you want. You can capture values by copy, just putting the name, the local name of it, or by reference by putting ampersand name, which means that if you actually want to update some value as you're iterating, then you can do so. So yeah. Okay. So then again, we need to use auto in order to, because this lambda doesn't have any defined type. You need the compiler to deduce that at compile time. So you need to use the auto if you're going to assign it to a value. And you just call this like any other function with operator bracket. So here's a simple example going to cout of just some function we haven't defined. But no, also know that because it doesn't have a name, it cannot take part in overload resolution. So just be careful there. Okay, question to you all, what does this do? No one wants to hazard a guess? This does nothing. We define a lambda with a capture with no captures, sorry, lambda with a capture with no entrance, with no arguments, the function body that does nothing, and then we instantly call that. And this gives obviously no return. Yeah, so uses pass small one-off pieces of code in freely into the algorithms, or similar. It doesn't just have to be these algorithms you can use this for, but this is a good use case for lambdas. So here we are sorting molecules from beginning to end. We're taking a constant reference, so we've got no captures here. That's why the square brackets are empty. And we're passing a molecule, comparing A and B. It's by constant reference, as in the arguments, and we're turning some Boolean based on this comparison. We can use it to use some complex initialization on something, especially if it should be constant. So here we have a constant set of random numbers. So we want to generate some random numbers, but we want them not to. We then want to set them as constant, so they can't ever be edited once we've generated them. So this assumes that we've got some local value size, which we're passing into the capture by reference. We've got no arguments that we're passing into this particular lambda. That's why the round brackets are empty. We're then using this to find return time to say that this will return a standard vector of floats. We then define our output answer as a standard vector of floats of size, which we can do because we've captured size into lambda. And then we do have a for loop. We're going to go through a random number generator and generate elements of the answer vector and return this. Note that we just instantly call this with no arguments. This is called I think it's an IFI, an instantly, basically a function that you call as soon as you define it. This returns then exactly what you want, which is a set of random numbers that you do not, you cannot change or edit, which is once you set sort of a chain, you don't want someone to affect this in your code. So this is another useful example of how this type of functionality can allow you to return certain types that you desire. Okay. So be careful what you capture. There's some rules of thumb here. So if your lambda is used locally, including pass to algorithms, capture by reference. This ensures there's no copies and ensures by any changes made propagate into your state later. Otherwise, you could change your captures and then they will go out of scope in the lambda and will have no effect on the program as a whole. So if you use the lambda somewhere else, make sure you capture by value to make sure that you don't have references that you then affect or invalid in the function when it returns. So references to other objects may still be valid, but it's hard to keep track of. You don't really want to be keeping track of that if you have to pass this somewhere else. You want to copy things, so they're kept with the lambda itself. Keep them short, as these are not meant to replace functions. These are meant to improve code locality and readability, but offer some state and some function like calling syntax that you get with functions. Okay, performance could be a consideration. So we've now discussed a number of ways to iterate. So we had 3 before we started this, right at the beginning of this session, and now we have a 4th. So how do iterate that? So how do these compare effectively? So if we can do this quick example, and is there an overhead is the main question here. So we're going to have a main function which is going to have some size and pass in, and then generate a float of data. We're going to call a random numbers, and then we're going to scale through a for loop and see the time it takes to do this scaling for each of our examples. These 4 examples. An important thing here to say is that so this is with a no compiler optimization, so -0, 0. So you're telling your compiler not to help here, and you can see that the C star is winning sort of for loop where you define everything explicitly, and everything else is similar. But as soon as you tell your compiler to do sort of medium level optimizations, that everything kind of sits on top of each other. It's not clear why the range style is slightly slower here. This could just be, they should all really sit on top of each other. But for anything of a reasonable size, they are, you're not losing in performance by choosing the algorithms as an option over explicitly writing out all your for loops. So that's what sort of a rule of thumb in terms of performance considerations is that this shouldn't really have a large effect. Okay, traits. I'm going to briefly cover this, but then what we'll do is we will look at the next example and let you guys work on that while I'm here to help or answer any questions, and then maybe from 12 we'll go through that today, but maybe half an hour is not enough time, so I'll probably come back to my morning and discuss that. So this then talks a little bit about how we can use types of use traits of types to do generic programming. This kind of goes back to some of the discussion we had around templating earlier. It's the if then else of types. You can then sort of configure your classes based on the type information you can get out, and there's some helper functions in order to extract this information. Okay. So several headers contain these type traits, a lot of information for handling types themselves. So is this a pointer? Has a value of false. If you apply this to an int type. So then you have things like standard numeric limits on some template T. Gives you lots of parameters on the for the built-in number of types, such as the largest, the smallest values, where the integers. Sorry, I thought someone's asked some question. Whether they are integers or floating types, other traits which used everywhere behind the scenes for efficiency. So this allows you to start conditioning and finding information about the types of the objects you're using, or the types themselves. So one example here, for those who are a little bit more used to sort of high performance computing, who will understand the concept of what MPI is. This is what's called a message passing interface, and it has its own type for float, a type for double called MPI float. So you may not want to, but what you'd like to do is, this is a library you're using, you want to keep this separated from the rest of your code. And since the code kind of knows the types already, then you want to keep this separated out with some interface.
And here we just have a simple queue to communicate. So what MPI does is it passes information between two different nodes on the computer or two different computers. And it allows you send and receive routines. And here we're going to have a class communicator. It has a function called send. And it's going to send some data in a vector of some template type T. And you've got a destination, and you've got a sort of message label called a tag. And here we've got some simple data. We've not defined what the tag is, it's just some integer value. So we have this function called MPI send. So what we've got is in this communicator class, we're wrapping around a MPI send. And we've got to pass in a data type. But we need to pass it in a data type that MPI understands, the library understands, which is one of its own MPI data types. That's a very simple implementation. So how do we fill in the correct type? We don't want to have to write for every single version of this, a version for int, then the correct MPI int, because there's sort of a large number of these. We don't want to provide a specialization for each. Because every time there's sort of lots of MPI calls and say n types to be wrapped, so we then end up with m times n specializations, and then this becomes complicated and a lot to maintain. So instead, what we'd like to do, create a traits class that tells our function how to handle different types effectively. So this is the data types. So this class here is a structure with the data type traits and has a static MPI data type. Okay. And what we say is based on, so now our com send doesn't, again, an explicit data type that we put in the code, it knows how to go get a type based on some T instead. And what we need to do then is just write a number of these, just have a getter that return the correct MPI type. And we can then use this to reduce the complexity in our writing of this wrapper function, this set of wrappers around the MPI class or MPI functionality. So you can start to use on these sort of traits to understand how types are related and do comparisons. And this can be quite powerful for doing more generic programming and conversions between certain things, as we've shown here. Okay. I think what would be good to do now is give you guys some time to look at the next exercise, which is going to focus on, let me just get to the right example, algorithms. Which is not coming up. Okay, right, 1 second. So it's this example here. So what you want to do is go through, so this is in the Git repository, it's exercises algorithms, and it's just ex.cpp. And what you're effectively doing is writing some transformations, and it's to a set of random numbers, and
applying the algorithms in a number of ways to sort, transform, and filter this data that's generated at the beginning in order to get a particular output. So effectively what we want to do is end up finding a number of the basically eventually going to calculate members of the Fibonacci sequence using algorithms and lambda functions, and filtering that down to a certain set of them. I think it's the even members of the first 47 or something like that. And you should be able to do this all within sort of a couple of lines in each section using the algorithms that are available and the and some lambda functions which you write yourself. The reference for these is sort of to look at online. I'm putting in the chat now, which are C++ reference algorithms and numeric algorithms. Will be very, very useful to you. And basically have a go. And in half an hour, about 12:15, I think we'll come back and at least have an initial discussion of this and see how people are getting on. And then I will come back tomorrow morning at the beginning of the next session and discuss the solution and go through some examples. But are there any, before we do that, are there any questions from the material we've covered here? I know that's kind of three kind of ideas here around the standard algorithms and how another way to do iteration through containers, lambdas, and then the trait system. But yeah, please send any messages in the chat onto the Etherpad, and I will try to answer them. But for now, let's have a look at this example. And I will put up this list for now as a good place to think about the type of algorithms you might need to use in that example. No, there isn't, but the best place for that would be something like Godbolt, the website. It allows you to write sections of code and run under various compilers. It also can give you, I think, the assembly for it as well. So it can be quite useful to use those type of tools for quick things. But no, there isn't an interpretive way to do this as far as I'm aware. That is one of the downsides of a compiled language. The thing you have is much more fine control over what each element is doing in C++ opposed to Python. You also get more errors when things don't. You have to be more specific with things like types, but this allows for the compiler to do optimizations, which can be very beneficial. So there's that trade-off. The reversed sort. So you can use something called, I think you could probably use a lambda. I think we had an example of that in the slides, which I'll now try and find for you. Give you a hint. Slide 21. The other thing to do there is a standard greater.
function which you can use. It's templated, so you need to pass a template argument. But if you look it up in CCP reference, I will do now and find you that. Give me 1 second. I'm just going to get this list of algorithms. Oh, sorry, I think you're right. I think I misunderstood your question there. Let me just find the correct piece of reference. Where was the link supposed to be? There's literally there's also this reverse algorithm. I have my wires crossed. So Denham says, when playing around with C, I found the debugger in code blocks. And similar functionality in other IDs helpful to visualizing what happens to variables as you work through change lines in the code. Not quite the same as the type of Python interpreter, but possible to sort of could be quite useful. Yes, you can compile with debugging flags, and then you can step through with the debugger. Those people who are coming from a Python kind of world, this is you set breakpoints and you can inspect as you work through the code's execution and see what the state of variables are at each stage. And then the IDEs, this comes from a set of command line utilities. Usually GDB is kind of the one that everyone is aware of. And then many of the interpreters give you nice graphical interfaces to this type of functionality, which can be quite useful and simplify you inspecting the state of your program at a given line. It's not quite as nice as say Python, because you can just run a particular place, but it does allow you to inspect in a similar way. And these sort of debugger type tools are quite can be very powerful. And then modern IDEs like blocks, or my personal favorite is VS Code. There's a whole variety. I think Atom also is quite well used that allow you to a lot of modules to
customize this functionality as you please, really. The other thing, feature functionality I kind of recommend for people would be things like IntelliSense, which when you end up with larger, more complicated code bases, can help to do some auto detection through to definitions or implementations of classes, which can help you navigate through your code a bit more easily. Okay, if people have had enough time to have a look at that, I will now try to work through it, show you some of the answers. So, so basically so a number of steps in order to demonstrate this sort of functionality and how you can use multiple of these algorithms together to demonstrate a result. So my mouse pointer is going haywire still, which is really not very helpful for you guys. Okay, so what are we doing? So we have a simple print vector function at the top, so we can output the result each time as we're going. I'm just going to make this to and first we have some vector of integers we're going to call nums. We have length 50. We've got one method of initializing them with some random numbers. So if we just make has already done all the reversing for us. No, it hasn't. It's just printed everything. Yeah, so okay. It's giving out multiple print statements because we've got them already here, but they're acting on the same vector nums, so it's having no effect. So the first thing, so we've generated some random numbers. Can we do this generation using the algorithms? So we're given the hint to use standard generate. And we then can do nums in, and we can then use our lambda gen.
we've now got a different set of numbers from the ones before. Okay. Okay. That's kind of step one. Now we want to do a simple sort on the numbers. So we're going to sort algorithm. And again, it's very difficult to use to begin. And for these, rebuild, execute. So now we can see we have the first output now is sorted, opposed to just being whatever the random number generator output given output has. So next is we want to do reverse sort. And be using sort on another here. So we want to right. So here we just standard sort and start the big end. And then, as we put in the chat a minute ago, we run standard standard generate. Sorry, standard quick done. Is type. We're going to do both of them here, and then the other one is instead we use. So let's sort of make sure that we're actually correcting ourselves. Otherwise, we're just going to reverse a reverse. That's going to be giving something to get back first. Sort. And then we can run standard reverse. Use the reverse function instead. So just file and recompile. So now we can see we've got two ways. So we've got first we've got sorted numbers, and then we've got reverse A and reverse B, and we can tell we're printing based on the code on the left. We've got reverse sort B, reverse sort A. Okay. So now let's look at a more involved example. So we're working through projects. So there's this group called the Euler Project, which offer a number of problems you can work through. If you've not come across them, it can be quite interesting to test out your skills and learn practice. Basically, offer a number of problems that you can work on. So the first thing we're going to do here is look at the Fibonacci sequence, and we need to generate it first. Just clear this. Looking at. Okay, so for this, we have a vector Fibonacci which has 47 elements. 47 we picked. We need to provide first a couple of elements in the sequence. And then we need some way of generating them all. So let's find what is it. So this is where we're going to use standard transform. So first of all, we're going to use
At the start, at the beginning of the Fibonacci sequence, and we're going to go to Fib's end. We're not going to write to the end, we're going to go 2 off of that, so that we don't overrun the vector. And we'll see that in a second. And we're going to, so this is going to be input. And we're going to start with these 2. We're then going to output into, but we're going to start now with the second one, because we've already defined what the 0th element and the first element values are. And we don't need to provide a function for that. Now I just try to remember if I did this with a lambda or whether I actually did this directly. Okay, you can write a lambda, but we're going to here use, so you can see we don't have an end here, because we know the length that's going to be operated on is going to be the same. Each input, we're going to get an output, as we expect. So, but the output's going to run from starting at the second element, and therefore the input can only run up to the 2 before that, otherwise we're going to overflow the vector. And then here we just use standard plus for an int. So again, this is templating, and that should generate the Fibonacci sequence. So we can that. Made an error. Interesting. Plus int. I ran this yet a day ago, and this is all fine. So this is the joys of live demonstrations. They always go wrong. Missing a library is usually the oh yeah, no, sorry. So this plus takes 2 elements as input, and therefore we need both. Sorry, it's going to give. We have begin. Yeah, so we need set A. Yeah. Let me check this works and then experiment this is doing. Okay, so the plus operator is going to take 2 elements and then insert them in. So this is where we're going to begin, and we're going to take multiple values. So see here now, this is the Fibonacci sequence. I mean, we haven't printed a nice message with this one, but last you can see we have so many elements from 0, 1, all the way up. just thinking about this elements to transformation, let me just grab the correct reference from CPP and find algorithms. It'd be easy if I just use the chat where I posted them. Yeah, so it requires 2 arguments, and I was only passing it 1, and then transform has an overload where it takes 2. So just to show this here, has input, first input last, input first 2, which we're missing, and then output first, which is what we want to output the values to. Okay. Next, we want to get all the values less than 4 million. So I have fibs less than a new vector, which is just it's less than the default. Then we are going to use a copy if. Just for briefness of time, I'm just going to give the answer as typing it aloud. Effectively, what you're saying is copy from fibs, the fibs end, and then insert this result into fibs less based on a lambda function, which takes in a single value x from fibs, each element, and does a comparison. And if this is true, then do the copy. Okay. And then print fibs less. So again, if we just so now we see we have a truncated set of fibs with some upper limit. Finally, then want to do the comparison for evens. And we can use the same approach again. We can copy if between the fibs. Now we're looking at fibs less, is our result to our previous output. I'm back inside a new vector evens based on a comparison based on the lambda that we've written, which takes in no captures and a single integer, which is the element from dereferencing each of the members of. So these are the members of the fibs less vector, returning true or false based on whether this is an even or odd value. So we have all the even values. I think we want to finally just do an accumulation. And for that, we can use one more of the here. This. And again, we can just accumulate over the evens, which is a result from the previous algorithm call, to then calculate the sum. Final thing, take this, run it, and then we get a final value of 4 million something, 4,600,000. And that's sort of a way you can use these algorithms to filter down and accumulate on values using this setup. Okay. I think we've come to the end of our time for today. I will drop in at the beginning of tomorrow in case there's any further questions. Please feel free to get in contact or leave messages or questions in the pad. and we will try and answer them tomorrow morning. If you have any follow-up questions, please do get in contact. And tomorrow's lectures will be on the Eigen library and on threading. Eigen is a very nice, especially for simulations of sort of matrix vector multiplication. It offers a lot of powerful functionality and flexibility for sort of scientific applications, quite commonly used. It's very nice. And then threading is around getting performance, and those will be taught tomorrow at the same time. Thank you all for your attention today, and I will speak to you tomorrow. They are called algorithms because they sit in the algorithms library. They are functions, but they are library functions, but underneath there will be some algorithm that does a sort, or some algorithm that does a particular application. And these are kind of, this library contains a number of algorithms for doing those standard operations. I think that's where the nomenclature comes from. So you're right, they are just library functions, but they all relate to some sort of set, or some algorithm that's kind of a core piece of functionality, if that makes sense. Thank you very much.